We'll be looking at myopia, which is nearsightedness, and hyperopia, which is farsightedness. So this diagram shows how nearsightedness is corrected. Now, before we get into all that, for the normal eye, the near point is 25 centimeters. So if you hold a book at a distance less than 25 centimeters, you're not going to be able to read it. So the near point is the minimum distance from the eye at which you can see an object clearly. And that is about 25 centimeters for an adult. The far point is how far away you can see, and that's infinity. So we can see up to infinite distance. So for the normal eye, the near point is 25 centimeters and the far point is infinity. But when you have nearsightedness, the far point is affected. The far point is not infinity anymore. So this person can only see up to X meters. So there is no problem with the near point. The near point is still 25 centimeters, but the far point, instead of being infinite, now becomes something finite, maybe 3 meters or maybe 2 meters. So that's nearsightedness. Let's work out a problem on that. So I'm just trying to summarize again. For a normal eye, the near point is 25 centimeters and the far point is infinity. So that's what's coming up there. Okay, and then if it's nearsightedness, the near point is still 25 centimeters, but the far point is not infinity. It is something, let's say X centimeters, and we are assuming that it's 300 centimeters in this case. So when you use those corrective lenses, the person should be able to see all the way up to infinity. So when you have those corrective lenses, what the lens should do is make an image of an object at infinity. And where should that image be? It should be X meters from the person's eye. Why? Because he or she can see anything up to X meters, isn't it? So as long as the lens, the corrective lens, which we're going to see shortly, is a concave lens, as long as that concave lens can produce an image X meters away from the eye of an object at infinity, this person will be able to see clearly. So when the object is at infinite distance away, the image must be at the person's far point, which in this case is 300 centimeters. Therefore, when we use the formula, 1 by f is 1 by do plus 1 by di, we're looking for the power of the lens, which means we need to get the focal length. This is what we get. 1 by infinity, because do is infinite distance away, di is negative x. Oh, that's crucial. Why negative? Because here we're talking about we are talking about virtual images. Here we're talking about virtual images. That means di must be negative. The person can see, but this cannot be produced on a screen. So we get 1 by f is negative 1 by x, or f is negative x. In this case, f is negative 300 centimeters. So that means whatever the person's far point is will be the focal length of the lens. So that is easy. And once you have it, you can find the power. But remember, when you calculate power, the focal length has to be in meters. Has to be in meters. Yes. So finally we get 1 by negative 3, which is negative 0.33 diopter. Now for hyperopia or farsightedness, what happens is the far point is not affected. The far point is infinity, but it's the near point that is not 25 centimeters. So this person now has to hold the book far away from the eye, because the near point, instead of being 25 centimeters, is now something bigger than 25 centimeters. Okay? And it's corrected using a convex lens, because we're going to see that the power is positive, and unlike the last case where the power was negative. So here it's going to be positive. Just summarizing that the near point normally is 25 centimeters and the far point is at infinite distance, right? We've seen that normally. That's the case. So if it's farsightedness, the near point is the one that's affected. So let's say the near point is x centimeters. The far point is still at infinity, and that x will again consider to be 300 centimeters. So that means the lens, when the object is at 25 centimeters, so this person should be able to hold a book 25 centimeters away when the person is wearing those glasses. And what the lens must do is take the object and produce its image at 300 centimeters. Why? Because this person can see anything up to 300 centimeters, right? Okay, so if DO, so again, remember the image is virtual. The object is at 25 centimeters, so DO is going to be 25 centimeters. DI is going to be negative 300 centimeters in this case. Negative 300 centimeters because it's virtual. And then find the focal length using the same formula that we've been using. Rearrange, plug in the numbers. So 1 by 25 minus 1 by 300, that's 1 by f. And then you have to find the focal length, which is the reciprocal of that, which comes out to be 27.27 centimeters. And then we find the power, but remember, focal length has to be in meters, so it's 0.2727, and you get 3.67 diopter. So see that the focal length and the power both are positive.